Well, hey, Bilal. So we had that problem from earlier, the permutations problem where we were trying to permutate 1, 2, and 3. And I found a great solution, which in our answer obviously was 1, 1, 2, 2, 3, 3, and then 2, 3, 3, 2, 1, 3, 3, 1, 1, 2, 2, 1. And basically what these two beginning function numbers are remaining the same. So it's kind of like we're choosing this number and then calculating the permutations for the the rest of the numbers. We're choosing this number, and then we're choosing this number. The one goes there, and then these are obviously the permutations of what would be here. And so, like I said in the call, we were able to do it recursively, but what I was looking at, I'll send you a link to what the solution that I found, but made a lot of sense. It was actually very simple to implement, but it was kind of like we have a decision tree saying that if we're given this array of 1, 2, and 3, then there's three possible decisions to make: 1, 2, and 3. And then from our 1, if we're at 1, we're at 1. Then there's two possible decisions to make from there. And it would be a 2 and a 3. And then the 2, there's a decision to make, which is a 3. And then from the 3, the decision to make, which is the 2. And likewise for these, we have two decisions that we could possibly make: a 1 and a 3. And the decision from the 1 is the 3. The decision from the 3 is the 1. And then 1, 2 goes to a 3. And then, excuse me, 1, 2. And then from there, we could choose a 1. And these are actually the answers right here. These decision trees, which is just a way to visualize how we can make this work. And I'll draw it out to also make it more clear right here. So if we're given a 1, 2, 3, then what we can do is we say take 1, and then we're going to break it down to a smaller subproblem, which is going to be a 2 and a 3. It's going to be a 1 plus a 2 and a 3. And then we're going to have a 2 plus a 1 and a 3. And then we're going to have a 3 plus a 1 and a 2. And then break these guy down. We're going to have a 2 plus a 3. And then a 3 plus a 2. Likewise. And what's interesting is that when we're at this kind of one element array, it's just going to be that element, right? Because a permutation of one element array would just be that element. And what's interesting about this is the amount of base cases where our array is equal to 1 is exactly the amount of answers that we have. This is equal to 3 factorial, which is 6. And the reason why I say factorial is because a permutation is it's a factorial. If the permutations of 1, 2, 3, then the amount of permutations would be 3 factorial. If it was 4, then it would be 4 factorial. We kind of talked about this on the phone, but it's almost irrelevant for what we're trying to accomplish here, which is we just want to solve this. So given this is kind of the solution on paper, I'll jump over to writing it out here.
What we're going to do is we're going to do it recursively, but we don't necessarily need a helper function. We're going to start by writing out our results array, and then we're going to write out our base case, which is going to be if the length of the array is equal to 1, we want to return it's asking us to, the question is asking us to return a list of all possible permutations. So if our array is equal to this, then a list of all possible permutations would be this. So that would be our base case when we're at the length of the array equaling 1. So we just would return the array at 0, which would just give us this. And now we want to loop through for I in range the length of the array. We want to loop through each of these, and what we want to do is we want to choose, kind of in our drawing, we want to choose this number right here. So we want to choose the first element, and then we want to choose the first element, and then we want to append that first element to all of the permutations, so that we have 1, 2, 3, and then we have 1, 3, 2. And so a way to do that would be, we want to get that first element. And so the way that we did it was creating a copy, which was array copy, and it was equal to the array from the array up to I plus the array I plus 1 moving forward. And we said our current number was equal to the array at I. And then what we want to do is we want to loop through the permutations of this array copy. So we need permutations. Let's copy this. Permutations of the array copy, which would just be passing in our array copy. Then looping through them for perm in permutations. We want to append to our results our current number plus whatever the permutation is of that number. And then we want to just return our results. So if we're going to go through this, we can kind of test it with our, we said to use a small value, so 1 and 2. So let's say our results is equal to this. We're going to, at I is equal to 0, we're going to have 1 being our current number, and then our array copy is just going to be 2, and the permutations of 2, since 2 is going to be a single element array, we're just going to pass in an array of, it's going to look like this, and we're going to say for permutation in permutations, which is this, we're going to append to our results array our current number, which is going to be 1, because it's going to be the 0th element of our array. We're going to append the results of this, so we're going to be appending an array to, we're going to be adding these two arrays, so that's going to be basically appending the current number, which is 1 and 2. So it'll look like that, and then the results, that will be appended. So the results will look like this. And likewise, now when we're at I is equal to 2, the current element is going to be equal to 2, since when I is equal to 1, the current element will be 2, and then the permutations of what would be just 1 would be this base case, actually. So now we have this as our permutations because we hit our base case and it returned this. And we're going to loop through these permutations. We're going to append the current number, which is 2, with this permutation. So we would actually have 2, 1. And we're going to append that to our result set. And because the length of the array was 2, that means we were at the last element in our for loop. So now we're going to go down to the results and return it. Going through the time complexity of this, it is interesting to me because we're going to be splitting our array. So this is going to have to be most likely a big O of in operation here. And we're going through the length of our array, which is also a big O of in operation, where n is the amount of elements in the array. Our permutation is going to be like a big O of in factorial, because the amount of times that we have to go through, like in reality, this function right here, its time complexity would be big O of in factorial, but we also have additional arrays here where we have big O of n, and then we have this. So I think that's where our time complexity comes from, where we have n squared times n factorial. And that's wrong. It is not n squared. It is n times n factorial. And then the space complexity of this would be at least n, because we're going to create a new array of results appending all of the permutations of n. And we said, actually, so we said if the result is going to be all of the permutations of n, then, and n is 2, then all of the permutations of 2, there's going to be a constant value times n factorial, because there's going to be n factorial permutations for an array of size 2, and obviously for each of those elements there's going to be n items in it. So I wonder if the space is actually going to be n times n factorial. You have to let me know what you think about that. But I hope that makes sense. When we run it, it passes. So yeah, let me know what you think.